Okay, good. I think you should be able to see my screen. Otherwise, let me know. So welcome back, everyone. So the goal of today is to try to correct this exercise, which, as I told you just before starting the recording, was quite long and difficult to do. And actually, one of the reasons was that simulations are slow because we are running alanine dipeptide in water, which is way more expensive. So maybe something that you could do if you want to run this exercise a bit faster, you could prepare a setup. It should not be difficult. You could prepare a setup with less water molecules. But we cannot, it doesn't make sense to do this exercise without water, so we have to cope with that. Another reason why it took some time to do it is that for fairness, I tried to run the solution using exactly the same version that we recommend to use from Conda, and that version is actually slow because it's compiled with the SSE optimization only. And so it's really better if you can to run these exercises with your own compiled version of GROMACS. Okay, so let's just go through them. I will assume that you have read at least all the assignments, and some of you I know have done also some of the exercises. So the first point was try to find which is a temperature at which events are happening. This is something that I would always recommend to do in advance. So it doesn't make sense to run straight away a parallel tempering simulation if you have no idea about what's going to happen when you raise the temperature. So it's very easy to just run a few temperatures in advance. And clearly the advantage here with respect to running the full parallel tempering simulation is that you don't need to put many replicas to make sure to have a large acceptance. You can even simulate, let's say, 300, 600, and 1000 just to have an idea. And then, sorry, another thing, here I have a notebook that I will use to show you the solution. I will not run it again. So I double checked before this correction that if I skip some of the boxes, those running the simulation, I can reproduce everything in a relatively quick time. But let's just scroll it for now. So here I have just some tools to properly run my simulations from the notebook. And this is an example MDP file. It's pretty standard settings. And the first test is just running simulations for a list of different temperatures. I mean, we can go through this box, but it's not so interesting. It's just, I'm just generating on separate directories input file to run for 1 nanosecond for each of these listed temperatures. Then we can just scroll down and see what's happening. So what I did then to analyze these simulations, I use PLUMED. You can do it in many different times. I just know how to do this quickly, so I can compute easily from a given trajectory. This is XCC file. I can, so you see I do a loop. I go to the directory corresponding to each of the simulations, and then I run PLUMED driver, and I compute a Colvar file. And then I use this read as pandas that if you never use, I recommend you to learn how to use it, tool to read a Colvar file into a pandas data frame so that you can just plot your trajectory using meaningful names for the columns instead of having to remember what was stored in column number 1 or column number 2. Okay, here I have a graph with, maybe this should have been plotted with the fixed range from -pi to +pi. Anyway, you see at 300 Kelvin, nothing is happening. 400 Kelvin, nothing is happening. This is just going through PBC. You have to go up to 600 Kelvin to see some events in the first nanosecond. At 700, you have something more, maybe the same number actually of events. 4 here, 3 here. You see, it's not systematic. If you go to 800, you have a few more events. So based on this graph, I would say that 800 should be sufficient. You see, it's difficult to predict this because there is a lot of stochasticity. It's not clear to me. It's not obvious how much this number will increase as I increase the temperature. Anyway, based on this, I would say 800 is probably sufficient to see transitions between one state and the other. So what I did, for exercise number 1B, I decided to use as a maximum temperature 800. So those of you that made this exercise, so which temperature did you choose as a maximum?
I picked 700.
Okay, probably it's not so different once you run it with parallel tempering. So any other proposal?
I also picked 700.
Okay, I think it's fine, 700. And here I was placing 32 replicas. Just I didn't make so many tests. These are also expensive. And again, this is just some trick to generate all my input files and run. This is really standard GROMACS. There's nothing special here. And here I was monitoring the acceptance with this geometric distribution of temperatures. I had an acceptance with 32 replicas that ranges between 25% to 45%. So I think there is no real hard rules for what this acceptance should be. So indeed, I was saying make sure that it's at least 30%. There is no way to prove that 30% is the right choice and not even 50% or 90% or 10%. This is very much heuristic. What really matters is then the autocorrelation times and how quickly your estimates are converging. Heuristically, I try to have an acceptance that is at least on the order of 25–30%. But I don't weigh any way to demonstrate that this is the optimal choice. Anyway, you see that for this range, you need a lot of replicas, 32. So clearly, this is going to be expensive calculation. And there is another very important factor to take into account here. It's very instructive. So when you have 32 replicas, so let's say that you have 32 replicas with an average acceptance of 25%. So it means, let's say, one exchange every 4 is accepted. So let's say that you exchange, in this case, I was running with exchanges with a stride of 0.2 picosecond. So it means that on average, there is an exchange accepted every half picosecond. So to go through a ladder of 32 replicas, you need 32 squared accepted exchanges because it's a random walk. So you need on the order of 1,000 exchanges accepted. So these start to be on the same time scale of the simulation time. It's like half a nanosecond. So I didn't do the full calculation of the round trip time. I think I was playing more with these types of analysis in a previous masterclass, so you can have a look there and do the same analysis that was explained there here if you want on these demuxed trajectories. But I'm pretty sure that here the round trip time is quite long, just because I need a lot of replicas and I need to go through all of them in order to go up and down. So this is going to make the convergence of this simulation very, very bad. Indeed, the truth is that I played this exercise twice with parallel tempering and I obtained 2 completely different results. I'm just showing one in this notebook. If you run it again, you will get a different result on this simulation length. So here I'm just analyzing all my replicas. I'm reading all my replicas to see what happens. And here I'm showing. So here I'm not doing any demuxing here. So it's difficult to know really how many events are there. But probably not many. You see that there are some time windows on which basically none of the replicas is on the second state. So one should probably do this with the demuxed replicas to really see how many independent events we can observe. And then, as I said, so I was suggesting to compute the population as a function of the temperature. This is what I obtained from this specific run. So the population of the second state, the least stable state, at the lowest temperature is very close to 0. And then it, as expected, it increases as I go up in the replica ladder. So I have to say that this happened on this run. Now I will show you separately the results of a simulation which is much longer. So this is, if I remember correctly, 50 nanoseconds per replica, same parallel tempering settings, and it's this one. It's pretty different. And you see that the population at 300 Kelvin is around 0.03. So it means that the population of the least stable state is 3% and the population of the most stable state. So those of you who were running these parallel tempering simulations, what did you find here? So something comparable to my long simulation or something comparable to my short simulation? How long did you run? Any feedback? Yeah.
Yeah, I ran for 1 nanoseconds, but I only tried with 15 replicas, and then the exchange probability was too low. And then I didn't run more replicas because I wanted to move on to the Hamiltonian replica exchange exercises.
Yeah, good point. It's a good strategy for this specific exercise because it was more important. Then other comments?
I had the same experience. I ran 16 replicas, so I had 16 core CPU, and yeah, I got exchange rates that are between 10 and 20%. So, and I ran for 1 nanosecond.
It makes sense. This is to show that even for a system as simple as alanine dipeptide in water. So since here you have a significant number of water molecules, I don't remember how many, maybe 500 or 1,000, I don't remember. Anyway, then you need a large number of replicas for a given temperature range, and the temperature range should be wide because we have a single barrier which is pretty high. So this is really not a good method for this system because you have a high barrier and it's easy to identify. So methods like metadynamics will work way better because you can bias this specific variable. Okay, good. So let's go then to the next point, unless you have questions or comments. We just go to this exercise number 2. So here, the aim was to learn how to set up this scaled simulation. So as we said last time, the first, so you have 2 things to do. One is to prepare correctly the topologies. And the second thing is to run a simulation with your scaled topologies. For the first step, you could use some alternative tools. And any of you try to do this scaling using some other tools different from the one that I provided? Okay, I think there are around a few tools, Python tools to manipulate GROMACS topologies that might be more flexible and more powerful. The one that I'm providing with PLUMED is it should work at least to do solute tempering with some caveat. And in particular, the problematic things are if you want to use charm with CMAPs. That's tricky. So if you are running your system with charm and want to scale the CMAP potentials, you have to look in the mailing list. It's explained how to do it. Anyway, these simulations for the exercise are with Amber, luckily. So let's go through all the steps. So first part is preparing this process topology. So this is just something with GROM-PP. How does this pre-processed topology look like? So let me maybe explore with a terminal, which is a bit easier than the notebook. 2210 solution. So it was 2A processed.top. So the difference is that this processed.top file contains all the force field parameters. It contains all the Lennard-Jones parameters for atom types, even atom types that were not relevant for this specific simulation. You see here. So this is self-contained. And then my awk script can, based on that, reconstruct all the terms in the potential energy. So the next thing that we have to do is to edit this file. So I have to specify which are the atoms that we consider as part of the solute. This is actually the very interesting part because you don't have just a flag to say, please scale the solute, but you can select individual atoms. It makes sense to select contiguous regions in the topology. But you can select just a few residues. So if you have a protein with 100 residues, you can select 4 of them, let's say, or 10 of them. Here I was scaling the full Solute, and so I was also preparing a script to be able to do it just from here. I don't know how robust is this script. Anyway, we can easily double check what happens, and I would really recommend to do this by hand, unless you have to do setups for tens of systems. So let me just go down to the adenine, which is here. So sorry, this is selected. Is it that one? Yeah, because this I produced it with my script, so it's not. There are other differences. Anyway, so the only difference anyway is that here I added an underscore to the name of the atom. That's not the difference. This is just conventional and used for my script to detect which atoms you want to scale. Okay, once you have done that, you can run this tool and produce a scale topology. It's useful to scale the topology with a factor 1 and see if the energy is not changed, because that means that this partial tempering script is doing the right things. Why is this part tricky? You see, in this selected topology, the one that you produce by hand, still you have that the generic force field terms are here. So you have like the generic dihedral parameters for these 4 types and so on. And then when you go down to your adenine, you have just the list of all the quadruplets of atoms that are feeding a torsional potential. If you go to the, so let me go to 2A, and then, sorry, that will be the 2B exercise. Topol scaled 1.0.top. Here, for the torsions, that's a critical part. You see that all the parameters that are general are commented out. This is to make sure that the GROMACS cannot see them anymore. And they are instead replaced here. So you have for every quadruplet of atoms, you have specific parameters. And there is a comment here telling you where these parameters have been picked from. So this script has to understand the way GROMACS picks atoms, picks the parameters based on the atom types. And this is subject to mistakes. So if there are mistakes, the energy will be different at this stage with respect to using the original topology. So this is a very important test, because this script is really far from being bug-free. So it's better to test this. And okay, now maybe many people have used it already, so it should be robust enough, but routinely I found people finding that some parts of the Hamiltonian were not scaled and suggesting how to fix the script. Okay, now you can look at the difference between the scale topologies with factor 1 and factor 0.5. So you see, basically, this scale topology contains additional atom types, which are atom types with the underscore, which are scaled down actually either by factor 1 or by factor 0.5. You see this is epsilon for the Lennard-Jones, it's half. So you have a lot of useless atom types because they are not used on this system, but they don't make any damage to the simulation. Then we can scroll down in this diff. We have differences in this is the part that is specific for alanine. So here you have the charges. They are scaled by a factor square root of 0.5. So the trick is scale charges by a factor square root of 1/2, so that the interaction is scaled by a factor 1/2. And then you scroll down and you see the dihedrals. Here, this specific factor, which is telling the amplitude, is scaled down by a factor 2. Okay, since there are many functional forms in GROMACS, it's tricky to make sure that the script works for all of them. That's why I'm saying to always double check this scaling. Okay, what do I do next? So this is just to see if we can generate the scale topologies. Then we can check if the topologies were scaled correctly. So the first check is rerunning with the scaled 1.0 topology. So this topology has been scaled by a factor 1, so it should lead to an identical energy. And I recomputed then all the columns of the, I'm printing here on a text file all the columns that are present in the EDR files. and reading them and plotting them. So you see, I'm plotting the difference here, the energy with the scale topology compared to the energy with the non-scale topology. I was a bit surprised. There's some difference in the long range part. It's very small. It's like, you see this here, the scale is 10 to the minus 5 kJ per mole. This is certainly not important. I'm not sure where this comes from. Maybe the number of digits that are written in the top file are not sufficient. But anyway, this is totally irrelevant problem. Okay. So did you manage to make this test, and did you find something similar? So if you follow all the procedure for this system, you should not find problems unless you made mistakes running the scripts. On your system, you might find problems if there are terms in the potential energy function that are not understood properly by my script. The next test is also very important, is to see if my script can not only interpret the general force field terms and bring them back to the molecule-specific terms, but also to scale them properly. So let's say that there is a new dihedral type that has a different number of columns. My scale will not treat it properly. My script will not treat it properly. So here I was suggesting to scale by 0.5, and then I was a bit confused in watching the number first, so I decided to scale by 0.1 in this example. You should get similar result if you scale by 0.5. Anyway, so here you have topology scaled by 0.1, so energy should be 1/10, not 1/2. I again use this rerun to recompute energies on my trajectory. It's important that you rerun again with the two topologies on the same trajectory, so that you are sure you are using the same numerical precision in the trajectories to compute your energies. And then here I'm showing the energy. So for all the 12 columns okay, except for the first one, which is time, for all the columns in the input file, I'm showing the ratio between the energy not scaled and the energy scaled. So if I remember correctly, here I have bonds, angles. They are not scaled by my script, so that's expected to be a factor 1. And then I have torsions and other 1-4 interactions and so on. I don't remember which order exactly. You see all of them are very close to 10. That's fine. These mistakes are not important. They are numerical errors that are fine. You see, it's critical that these differences are very small. Again, these are kind of bigger. This is the sum. Okay, I think it's fine. Still, maybe I should double check these numbers, why they are a bit bigger. They are still probably the problem is the number of digits with which the energy itself is written. And so when you compute the ratio, maybe there is some problem. Okay, did you perform this test as well? Did you get something similar to this? Did you find troubles? Okay, so let's go to the next point, sanity check on the replica exchange implementation. So there are two tricky parts. One, preparing the topologies, that's done. You can do it by yourself if you want, by hand or with some other tools. Second, being able to run with this -hrex option. And as I said, this implementation is very tricky. So you have to double check that it's working on your setup. And I would really recommend to run with the final setup, because Gromax is doing some fancy optimization. Maybe you run with I don't know, MPT, and it uses something. Then you go to MBT, it optimizes something, and then this implementation is not working anymore. So really do this on your final setup. So this is like a dummy replica exchange simulation where all the replicas share the same scaling factor. Acceptance should be 1. You see, it's 1. You can do even more. So you can check explicitly this dPlumed, which is written. It's the contribution of the acceptance coming from Plumed. And from this difference in energy, they are exactly 0. Were you able to reproduce this?
Yeah.
Yeah. Okay. Good.
This was able to happen.
Okay, good. So this means that so there might be problems, for instance, if you run on a GPU, if you use some advanced GROMACS option, I don't know, modular integrator or whatever. So we try to make our best to disable all these things automatically whenever you combine with Plumed, but of course, it's better to double check. Then there is an exercise which is equivalent to the one that we did with the parallel tempering, but instead of increasing temperature, we quoted the temperature of the solute. So again, I did this with a script. I just used a linear interpolation between 1 and 0.1. I went to pretty low factor here. I ran my simulations. I analyze each of them with Plumed to see transitions. And here are the graphs. So with lambda equal to 1, no transitions. Then as I decrease lambda at some point, eventually we'll be able to see transitions. So lambda equal to 0.5. This means like effectively like 600 Kelvin on the solute. There's one transition here. 0.4, one transition here. 0.3, one transition here. So you see, if you then convert this to temperatures, you see that this is less efficient than parallel tempering. So the same, so let's say 0.2, I have a few transitions that would be equivalent to 1500 Kelvin. Okay. It's less efficient because you are not doing anything to overcome barriers associated to water. So I suspect that there's maybe some hydrogen bond that has to form. I think there is this, if I remember correctly, this system, there is the same hydrogen bond that should form with a different orientation of the molecule. But you should break that and form an hydrogen bond with water. So the formation of the hydrogen bond with water probably is also slowing down this transition. And there might be other factors associated to water that are not accelerated here. There is another also contribution to consider. So I told you that scaling down energy or scaling up temperature is the same. That's not strictly true. So it's true if you look at the distribution, at the ensemble that you sample. On the other hand, it's the equivalence is exact only if you scale time as well. So let's say if you double the temperature, you are having an effect on the ensemble that is equivalent to scaling by a factor of half the entire potential energy. But in addition, atoms are moving faster. Okay, so there is an additional factor that I think is a square root of 2 in that case, in time, that makes, let's say, parallel tempering a bit more dangerous, more risky, because you are effectively trying to move the atoms faster, maybe with some risk on the stability of the time step, of the integrator with your time step. And on the other hand, you are gaining less. So if you scale the Hamiltonian, you gain less because you don't have this factor. So scaling the Hamiltonians is like safer because you decrease the forces instead of increasing the velocities. So it also has a smaller impact on the kinetics, of course. Okay, does it make sense? Any questions, comments?
So for like a real system of interest, besides doing the sanity checks to make sure the PLUMED script is working and we have proper replica exchanging, should we run, like, should we start with parallel tempering or to find like the right scaling value, or should we use?
No, I would not do it, because for especially, so if you are in a context where you are scaling the full solute, it kind of makes sense to use parallel tempering, but then it's more to like, it's like just if you want to show in the paper why you used a more sophisticated method and you didn't use the standard parallel tempering. But apart from that, I think it's not so interesting.
So then when starting from this step, like exercise 2D, we should be able, like running to find the right scaling parameter, the transition that we are looking for, we know should happen, we should be able to see here before we even bother running like exchanges, right?
Yeah, exactly.
Okay.
Yeah. Then one thing important is that you can always combine this method with metadynamics or even umbrella sampling. It's a bit tricky, but you can combine with biasing on specific variables. So I would say this system here is really bad for the method. So if you combine with metadynamics on phi, everything will work like a charm. Okay, so similarly, in your system, you might be in a situation where the scaling on the Hamiltonian is not sufficient to see the transitions. So maybe something that you could try is not just scaling with Hamiltonian, but maybe scaling the Hamiltonian plus maybe metadynamics on the variable that you know you want to bias, see if things are happening faster, and then you run with multiple replicas to make sure to sample the correct ensemble. Okay. Or if you want to use just pure replica exchange, then you have to find the scaling factor so that events are happening at that scaling factor. Otherwise, there's no point in interpolating between that number and 1. Other comments, questions? Okay, good. So here I decided to use 0.15. Something in between the last 2 factors where I had number of transitions. It's pretty arbitrary. So honestly, I think I never used in practical applications factors that are that small. And again, this is because of the choice of the system. I think this method is not good for crossing barriers that are on the order of, is this 10 kcal per mole, I think. It's really not the right method. So it's better to cross smaller barriers where you can cross them with more moderate scaling factors. But if I want to solve aniline dipeptide in water, I have to go to a very low scaling factor. Then you could compare the 0.15 with 300 divided by 800. It's kind of comparable, but it's smaller. So you see, you have to, or in other words, you have to go to a higher effective temperature to see events. This is expected. On the other hand, we will see that you need way less replicas. Okay, so next point, exercise number 3 was running Hamiltonian replica exchange simulations. Now I decided to use this minimum value 0.15. I empirically use the linear spacing. That's what I did in many real applications. So I thought to do it here, but then actually in the next exercise, we will see how to optimize the ladder. And I realized by preparing this exercise that it's actually easy. So once you have done all the implementation, so I never did it before, but I think I will do this in my future works. So in the past, I always used this linear spacing because I've seen that empirically for me, it was giving more uniform acceptances with respect to geometric scaling. But of course, this could be system dependent. Anyway, let's use this as a starting point. So I just used to generate a ladder of lambdas. Then I have this script to just create my scaled topologies. So you see, you edit the topology once to select the atom, so you have to do it with a lot of care. But of course, you have to rely on this thing done automatically to scale your replicas with different scaling factors. So you have to make sure you do things properly. And whenever I do this, I always go there, double check, take a diff between different directories, see if I really modified only the topology and so on. It's easy to make mistakes. Okay, this was done with a larger stride between exchanges. The truth is that I was first running with a larger stride, and then I had problems in the parallel tempering simulation. I tried to see if I could solve the problem decreasing the stride. I went back and I ran again with a lower stride. This parallel tempering simulation is really expensive. The only solution was to run it much longer. So, okay, this is my setup. I run my simulations. These are my acceptances. So did you find something like that? So what I see empirically here is that the linear distribution is not giving uniform acceptances, especially in the regime where the scaling factor is very low. And as I said, in practical application, I never go with scaling factor like lower than 0.6 or so. So I never realized this, but clearly it's a bit suboptimal here in the lower part of the ladder. Still, I think this is pretty reasonable. 10% could be fine. Notice now I have only 5 replicas. So if there is a random walk, so if I assume exchanges to be uncorrelated, I will need 25 exchanges multiplied by the inverse of the acceptance, so maybe around 250 exchanges to have a round trip. I have many more exchanges in my simulation, even with 1 nanosecond simulation. So I think this is fine. Then I read my trajectories as I did before. And this is the lowest. Sorry, no, these are all the replicas. And again, with mixed colors, so you cannot see the real transitions. Not many. So probably the fact that the overall occupation of this state is lower is just because in the highest replica, it's less occupied than it was in the parallel tempering simulation. Still, there are some transitions at least. And okay, you have to consider that this is way less expensive. It's only 6 replicas instead of 32. I was just checking the distribution on Psi. You see the distribution on Psi is not exactly uniform, but kind of uniform already. So this is to say that doing metadynamics on Psi doesn't really make so much sense, will not help much on this system. So, and here I'm plotting the population. So again, I'm computing, I'm just counting number of frames between 0 and 2, and between 0 and 2 is here, between 0 and 2. I call it state B, all the rest I call it state A, and I plot just the ratio between them. And you see I get a line like this one. So population of the higher energy state is increasing as I go up in the replica ladder. Here I'm plotting to make some comparison this effective temperature, let's say, which is the simulation temperature 300 divided by lambda. And here I have the corresponding graph from parallel tempering. So they are similar just in the fact that they are both increasing. As I increase the temperature, the population of the B state increases. If I look at the long simulation, maybe I can do a bit more quantitative analysis. So you see, these are both simulations are 50 nanoseconds long per replica. So I actually trust much more also the yellow one, the orange one, which corresponds to the Solute tempering simulation. So you see they both give a population, the relative population of 2 states, which is similar in the reference ensemble at 300 Kelvin. And clearly the slope is different. So by increasing temperature, you increase the population in a way that is different from decreasing the scaling factor. And again, this is because you are not scaling the contributions due to the solvent. It's really, it's not, you don't have to think really at this as a temperature. So you are not really reproducing what happens when you increase the temperature. And so, yeah, you cannot, for instance, use this simulation to extract temperature dependence, compared with an experiment done at a different temperature, at least for this system. I've seen papers showing that you can do that. My impression is that this is probably system dependent. So I would be very careful in saying that this is valid for a general system. Questions, comments? Did you manage to obtain something similar to this at least? So one of the questions was exactly to compute these populations. Did you obtain numbers comparable to these ones?
Yeah, I did 10 nanoseconds per replica, and I did 4 replicas divided between 0.4 and 1 for lambda, and I think I got results somewhere between this graph and the graph for the 50 nanosecond simulation. So
okay, great. You see, this is 0.04, whereas this is 0.03. It's like kind of lower. See, so I think, yeah, probably you have a more accurate result than this one. And what about the dependence on the lambda? I don't know how to. So you said you arrived down to a lambda which was 0.4. So 0.4 means, let me do the math. or anyone can do. Let me do. So it would be 300 divided 0.4. It's 750. So let's try to go back. 750. It's here. So maybe the population could have increased, I don't know, by a factor 1.5 or so.
Yes, I think that's approximately true.
Okay, good. Okay, good. Next point, analyze. Okay, so exercise number 5 was not the optimization, was still 1. So one of you at least have done this exercise as well. So let's see how I did it. So this is just analysis. It's the same simulation analyzed here. So we discussed how to do WAM. What I call WAM here is actually binless WAM. We discussed how to do it in the previous masterclass. What you have to do is to compute for every frame of your trajectory. So you have to first concatenate your trajectories. For every frame of your trajectory, you have to know which would have been the probability to generate that frame in each of the Hamiltonians that you used. Okay, we were doing this with metadynamics with the assumption that I was calling it like final bias reweighting, which involves some kind of approximation. Here, I would say it's more rigorous. This is more close to what you do normally with umbrella sampling. You have static definitions for the potential energy function. It's just not a bias potential in the PLUMED language, but it's a separate topology. So what you have to do is you have to use this rerun to compute on the concatenated trajectory that I produced here to compute the energy according to each of the topologies. And then I'm just writing the total energy equal 11. Hopefully the total energy is the right column. Actually, I'm not using it here, but there is a very nice tool called PanEDR that you can use to read EDR files into Pandas data frames. I didn't use it here because it was not installed in the masterclass environment, but I would recommend you to use that instead of using eco11 here. Okay, and then, so in the end, what I have here is energies NumPy array, which the first index is the number of the frame. You see, it's 6006 because each trajectory is 1001 frames. I was maybe naively using the full trajectory. I would recommend in practice to discard the initial part. And each of them is 1001 frames, so times 6. So you see, I have for every frame the energy according to every topology. So I have 6 for the second index. I just feed this to the WAM script. So for have this working, you should use this WAM script that has some improvement with respect to the one that is provided in some other tutorials and works well even if you have very big energy differences between different Hamiltonians. It has some numerical tricks to just subtract the maximum and add it back at the end. So it allows you to basically pass directly the energies to the script. And these weights are the weights that you obtain are not weights associated to any specific ensembles. They are, if I'm not wrong, just like the logarithm of the density of states they represent. So you can basically obtain from these weights, the weights corresponding to an arbitrary energy function by multiplying by that energy function. Or since it's a logarithm, by subtracting so by multiplying by the Boltzmann factor associated to that energy function, or by subtracting energy divided by kBt here. So in this way, I obtain the weight, the logarithm of the weight associated to the ensemble number 0, so the first replica, the reference replica. I subtract its maximum just to take the exponential, and normalize. These are the weights that allows me to compute from the concatenated trajectory averages corresponding to the first replica. I can plot these weights. So I didn't do any demuxing analysis here. If you go back to masterclass of last year, you can really try to do this demuxed analysis on this trajectory. It should work in the same way. It's also instructive to plot the weights here. Why? Because here, since it's not demuxed, you can see like this is first replica, second replica, third replica, because they are concatenated one after the other. And so you see that the weights do make sense. Actually, they are high. So the frames that were generated in the first replica have a high weight when you try to produce averages that corresponds to the first ensemble. The frames generated from the last replica as a low weight, they are typically irrelevant, which also maybe tells you that it's not so useful to do this WAM analysis. Okay, except for the first frame. Why? Because the calculation of this weight only depends on the structure. So it doesn't depend on from which Hamiltonian the structure was generated. So clearly, the initial structure was equilibrated using the reference Hamiltonian, so it's good for the reference Hamiltonian. It has a high weight in the reference Hamiltonian. Then, as the system equilibrates, I think equilibrating this requires a few picoseconds. So after a few steps, these weights become negligible. One important thing is that you realize here that you have significant weights only for the first few replicas. That's related to the acceptance rate. So typically, if you work in a regime where you use the minimal number of replicas required to have an acceptance rate, let's say, I don't know, 10%, and let's say the acceptance on the second neighbor would be completely negligible, typically these weights decrease very quickly. Or in other words, it's not necessary, it's not helpful to do this WAM analysis. One thing that you could do, I didn't do it here, is to make this analysis faster. Let's say you could concatenate only the first two trajectories. Okay, pretend that you were using only two replicas. So compute an array which would be 2002 times 2 elements and do WAM on those. And then you will have only the first part of this graph here. Okay, so, and you can ignore these frames that you know a priori will have a low weight. Another thing that you can do here, you can plot this cumulative sum of the weights. This cumulative sum, the slope of this cumulative sum is like doing a average with windows. So you see clearly that there are these kinks. So clearly the average of the weights in this part of the concatenated trajectory is higher than here, is higher than here, and so on. So clearly you can discriminate, you can see from here where is the jump between one trajectory and the next one. So clearly the weight is systematically decreasing as you go from one trajectory to the next one. And here I can do the same analysis for the computing the population as a function of the effective temperature. And I get actually a very similar result with the WAM, with respect to using just a single replica one by one. Okay, does it make sense? So I think at least one of you did this part. Did you find something similar? Were you able to arrive to the end?
Yeah, I stopped at the last part of this exercise I made was the weights versus frame number graphs, and then I stopped because I was running out of time and I wanted to move on to the last exercise.
Okay, so but did you find something like this?
Yes.
Okay, I think below I was also plotting. It's nice. You can show the weights to corresponding to ensemble 0. You can easily compute the weights corresponding to another ensemble. Okay, I didn't show you how to do it. It's here. So you can easily, once you have these weights that bring you back to the ensemble number 0, you can easily convert them to ensemble number 1, number 2, number 3, and so on. And you can compute the weights that allow you to compute averages in ensemble number 0, 1, 2, 3, 4, 5, as expected. So the frames that are at the end of this concatenated trajectory are good for doing estimates at high effective temperature. Okay, good. Then optimizing the Lambda ladder. I think this is something very useful that I learned how to do it while doing this exercise. So there's one thing that you can realize that with this expression of the energy as a function of lambda, energy is a quadratic function of lambda. Why? Because there are parts of the energy that are scaled with a factor lambda, parts that are scaled with a factor square root of lambda, and parts that are unscaled. Okay, so actually it's a quadratic function of square root of lambda. That means that you don't even need to do these reruns over the 6 topologies. You can just run them over 3 topologies. Fit a parabola and use that parabola to predict the energy for any arbitrary topology with any arbitrary value of lambda. So I was already computing this for 6 topologies, so I can check this. So this is just for one of the topology, I have this behavior. This looks like for most of them, for most of the frames, sorry, this is for one frame, frame number 100, energy as a function of lambda. In most cases, it's going to decrease in this way, but you can cherry pick cases where this is also increasing, for instance. But whatever you do, you will always find points placed along something which is a parabola if you plot it as a function of square root of lambda. Okay, so you can do a fitting. Here I have a loop over all the frames. For every frame, I find the coefficients that allows me to compute energy as a quadratic function of square root of lambda. Okay, I accumulate these coefficients, and then I can use them to compute the residuals. I can see how different are the actual energies from those that I fitted. You see, I have 6 points. If I had 3 points, it would be a completely trivial exercise. I have 6 points. But the residuals are very small. Okay, which means that these 6 points lie on a parabola. When I say very small, I mean these are energies, so they are much smaller than KBT. So actually, any mistake on this order of magnitude is not relevant for what concerns the calculation of weights. Okay, so that means that I could repeat the exercise before with many less of these rerun operations, with only 3 of these rerun operations. Okay, just find the coefficient using 3 values of lambda and predict the other ones. But I can do even more. I can predict also results for intermediate values of lambda. Okay, and then I wrote this tool that is able to predict the acceptance given any pair of values of lambda. How do I do it? So I have my coefficients that allows me to predict basically the energy given any choice of lambda. So I have 2 values of lambda, lambda 1 and lambda 2. I have my coefficients. I compute the energy in the topology with the lambda 1, the energy in the topology with lambda 2. I again take my reference log weights and I subtract energy 1 or energy 2 divided by KBT. Subtract the maximum. This is just, again, the same trick to avoid divergence in the exponential. Do the exponential, normalize the weights. So at this point here, I have weights, W1 and W2, that can be used on the entire trajectory to predict the energy, to predict averages according to the ensemble with lambda equal to lambda 1 or lambda 2, respectively. Okay. Now I have to compute the acceptance. I did it in 2 different ways, but I would suggest this one to do a minimization. So I have to consider pairs of states from one ensemble and from the other. I did a double loop here. So I consider all the possible, oh, sorry, here I did it with a single loop. Yeah, you could do it with a double loop, but it would be more expensive. So here I did it with a single loop. No, sorry, again. I did it with a double loop. It's just that the second loop is implicit because it's written here with this averaging. So I want to do it with a double loop on the frames. That's why I'm using this skip. I'm skipping every 5 frames, which saves me a factor 25 in the execution speed of this. So basically what I do is I say I take the first frame from ensemble E1, the second frame for ensemble E2, okay? And then I compute the acceptance between these 2 frames, okay? I have to compute an average because I know the probability to extract the first frame from ensemble E1 is just W1. The probability in ensemble E2 is just W2, okay? And so you see I have to compute an average with weights W1. So I should do this with like an external product between the trajectory itself with weights W1 and W2. And the function that I should average is this minimum between the product of the probabilities not swapped, sorry, swapped, divided by the product of the probabilities swapped and 1. This is the formula to compute the acceptance. Does it make sense? Maybe one has to think about it. Maybe let me write it down in a way that is more readable, even if it's much slower. So I have a double loop, and then for each, so this is a double loop over pairs of frames. For each of them, I compute this. This will be the acceptance if I try to exchange between these two snapshots. Okay, but then I have to consider that the probability to extract the first frame from the first ensemble is W1, and for the second ensemble is W2. And then I return, I have to return, I have to return A. And I can do like this, A equal to 0 with a scalar. This is like an alternative implementation. Does it make sense? So what I'm doing here is just a faster way to do this. I sum over all pairs of frames in my trajectory. I use as a weight the product of the weight of the first frame in the first trajectory and the second frame for the first value of lambda and the second frame for the second value of lambda. And then I compute the acceptance if I were trying an exchange between those two frames, and I compute its average. Questions, comments? I can show you that it works. So the simplest thing to do is try to predict the acceptance between lambda 0 and lambda 1, lambda 1 and lambda 2, and so on. Those lambdas that I used in the simulation. Okay, you see these are my predictions. And then I can check from the log file which were the actual acceptance rates. They're very close. So my prediction actually is more accurate because it takes into account also snapshots that exchanges that I didn't try, like pairs of frames that I didn't try. So this estimate is more accurate than this one. Okay, does it make sense? So once I have this tool, I can use it to predict acceptance for any given pair of lambdas. I can try to see what would happen if I were using a geometric distribution of replicas. You see, now it goes in the opposite direction. The acceptance increases instead of decreasing. It's a bit more flat. It goes from 25% to 46%, but still it's not uniform. How can I make it uniform? So I think this I was sharing it already in the assignment. So what I was doing here, I was trying to do a minimization. I think one can do this a bit more efficient, going there and computing the gradients of the acceptance with respect to the weights. But it's more tricky and I didn't want to do it here. So I use just a minimizer that does not use gradients. So it takes many more steps. But it's fine. It's working here. So and then you do it this once. So what I'm doing basically, I'm fixing the first lambda to be equal to 1, the last lambda to be equal to my lambda mean. So the number of parameters in this minimization is 4. I have 6 replicas, so it's only the 4 intermediate lambdas. Okay. Then at every iteration in this minimization, I compute acceptance between the 1 and the first parameter, acceptance between the first and the second, second and third, third and fourth, and lambda mean. I take these 5 acceptances that I predicted, I take the product, and I try to minimize the product. Sorry, to maximize the product. So I was minimizing minus the product, I think. And this is what happens, that at the end, the predicted acceptance are very similar to each other, all of them very close to 33%. And here's the ladder of lambdas. I can plot the ladder of lambdas. So this is the, okay, it's in the label is wrong here. So this is the replica index. And this is the value of lambda. The linear interpolation goes from 1 to 0.15 linearly. The geometric progression goes here. The optimized one is here. Okay, does it make sense? So I think you should be able to adjust this script also on another system to be able to predict the best allocation for lambdas, just based on a short simulation where you compute the typical values for these energies. Questions, comments?
I'm still running, so I will try probably this week.
Okay, good. I think it's actually I would be happy if you give me feedback on using this on another system. One thing that I plan to do now is to do the math and compute the gradients, because this will make the optimization much faster. So you see, this in 4 dimensions, it works well with a method without gradients. If you run in systems where maybe the scaled portion is larger, maybe you need, I don't know, 16 replicas, you have to do minimization with 14 parameters. It might be much more efficient to have gradients implemented. So maybe it's worth to do once the math and find the gradients. But
another system, you also mean bigger systems,
so
like proteins and...
Yeah, and what's important is that the scaled part is bigger.
Okay. Yeah, because I do have my own system, but I wanted to try this simple first, just to make it work.
Yeah, if you try on your own system, manage to use this script in your own system, let me know.
Okay, I'll let you know.
Okay, good. Then last exercise, meta-dynamics on psi. This is a very bad exercise because actually this psi is a very bad variable for adenine dipeptide. And as expected, the results are kind of not very satisfactory. Also, this was running for only 1 nanosecond. And it turns out that, let's go down to the results. So first, what did I do? I just used the same identical setup that I used for the exercise 21.5. So meta-dynamics on psi. And then I was bravely going directly to the WAM analysis. But let me first show what happens if you don't do the WAM analysis and you just take, okay, first exchanges as predicted, very uniform. Good. I read my trajectories. I have transitions, not so many more transitions, actually. Actually, meta-dynamics on psi is not helping at all the transition on phi. The distribution on psi is more uniform than before. Here's the WAM analysis. Let me go first to the non-WAM analysis. The non-WAM analysis is just, okay, no, I have to do it in this order. So how to do the WAM analysis here? Remember the philosophy of this WAM. You have to know which would have been the energy of each frame according to the Hamiltonian of every replica. So for the topology part, we know already how to do it. You have to use this rerun 6 times, or now we learn how to do it in theory doing it 3 times only, if you want. But anyway, you have to produce this energies array, which contains the energy according to every simulated value of lambda for the concatenated trajectory. But there is an additional part, which is the bias that you would have had according to another replica for every single frame. And to compute this, we use the same approximation that we used in the other masterclass. That was the final bias approximation. We just read the hills and do a fake restart. And that's explained better, I think, in the meta-dynamics masterclass. I do a fake restart with adding no more hills. And I just compute the bias as a function on psi for all the frames on the concatenated trajectory. Then what I should feed to the WAM script is energies. So, and again, this bias is also number of frames times number of replicas, because each replica has grown its own independent, psi-dependent potential. So what I should feed to the WAM script is just the sum of the two. contributions. That's the potential energy function that I use in the simulation, with the exception that I'm cheating. Actually, this was the definition of the potential energy function at the end of the simulation. Okay, but we know that empirically with metadynamics it works to assume that the bias was statically equal to the last version. So then I feed this sum to WAM. I compute the weights. I want to compute the weights in the unbiased distribution without the metadynamics potential. So I just subtract this. So if I imagine to do this with a single replica, this one just returns me something like the weight would be e to the plus beta times the bias potential. So you see here times the energy that I feed here. So here it would return me e to the minus beta energy plus bias. I remove energy, I get e to the plus beta bias. That's the usual way with Reweight metadynamic simulations. Okay, but here I have the advantage that I'm combining from multiple replicas. With the exception that the result that I obtained was not very satisfactory, because I say, okay, here I find 0.02. So it should be 0.02 or 0.04. And actually with the long simulation, I see that it should be something like 0.03. So probably both simulations are not long enough. And what I'm seeing is that this is not correct. The previous one was not correct, but in the opposite direction. And so they are both equally far from the correct answer. Then what happens when I look at the dependence on the temperature or the scaling factor? You see that, again, I'm comparing WAM and non-WAM from the same simulation. They are very similar. This new metadynamic simulation is different just because it's a different realization. And I guess that if I'm running this parallel temperature metadynamics for 50 nanoseconds, I should get something that is similar to what I get here with the Hamiltonian replica exchange add-on for 50 nanoseconds, basically because metadynamics on psi is not helping and not making any damage. Okay. Okay, I think we are done with also the final exercise. Does it make sense? Questions, comments?
You mentioned that using Hamiltonian replica exchange on instead of umbrella sampling simulations can be tricky, and I was wondering if you could elaborate a bit on that.
Yeah, because usually with umbrella sampling, I mean multiple restraints. So you have an additional direction on which you have to do multiple replicates, right? So the way to do it straightforwardly would be I have a restraint in a given position, and then I use hrex to do enhanced sampling. Then separately a restraint in another position. Okay, and we stressed a lot in the masterclass about umbrella sampling that it's very dangerous to do separate windows without replica exchange. So I would say this is not very robust protocol. It would be robust if you also allow exchanges between separate positions of the window. But then you need to implement a two-dimensional umbrella sampling. So it's not straightforward to do it. It's not implemented. You cannot do it with the current implementation. Other comments, questions? So anyone that had the time during this week to also try some of these on his own system and maybe found something interesting that is willing to share? Okay, good. So let me recapitulate. The very important thing is this part on these checks here. It was exercise number 2. And let me stress again in case someone is then listening to the recording and skipping the part where I said it before, you should do this on your own system, because the script that edits the topologies might miss some of the contributions that you have. So I don't know, maybe you have a Morse potential and it's not scaled or something like that. So, or a new form of the dihedral angle that was added in a recent version of GROMACS is not managed correctly. So be careful with that scaling. And also this minus HREX, test it. I would really recommend to test it on the same machine, even with the same queuing setting. So don't do something like your final simulation is going to use 4 MPI processes per replica, but you do this test on your workstation. No, do it on the cluster with the same number of processes per replica, everything the same, except you have all the topologies with the same scaling factor. And you don't add any time-dependent potential like metadynamics that would make the potentials different, so that you can check that actually the acceptance is 1. That's really important. And then, try to repeat this one. If you try this on your own system, try to repeat this one analysis, because it can enrich the statistics. Even doing this only on the first 2 or 3 replicas can help. Why? So typically people think, who cares about doing these simulations? These continuous simulations are anyway going up and down. If I miss something that was in replica 1, who cares? It will go at replica 0 at the next exchange. But there could be cases where the round trip maybe goes down to replica 2 and then goes up. So that state is missed. If you use one, you don't waste anything, except that it takes some time to do the analysis, and you gain statistics. So I see that it can be cumbersome to do all this calculation with all the topologies. So one thing that I recommend is just do this with the first few replicas. And typically, if you are running a setup where the acceptance are on the order of 30% for the first neighbors, you will not need, including more than 2 or 3 replicas, it's not helpful. So you can directly go with, I don't know, replicas from 0 to 3, and that's it. And this will increase the statistics. Another thing that you can do is to do this on the demuxed trajectories. This will allow you to do bootstraps on the demuxed trajectory, which is much more reliable to estimate errors. We didn't do any error estimation here because the calculations were already very long. But yeah, when you want to publish some number, you need to know how much is the statistical uncertainty. Yeah, and then I hope this final example showed you how to properly combine these weights coming from the multiple Hamiltonians and the weights coming from separate bias potentials added on separate replicas. Okay, good. So then if there are no more questions, then thanks again for participating in this and asking questions, and then see you next time.
Bye.
Bye-bye.
Bye-bye to everyone.
Thank you. Bye-bye.
Thank you.
Thank you.
Thank you.
Bye.